Okay, so I think then we can now move on to our morning presentation. We're very excited to have with us Professor Tali Figueroa-Feliciano from Northwestern University. I've gotten to know Tali through our work within the Quantum Science Center. He'll talk a little bit today about some of that and its connection to the intersection of quantum computing and dark matter. And I know that this is a really hot topic for us, so we're looking forward to that. Let's welcome Tali to the stage.
Good morning. Good morning. All right, we're awake. Good. So, my name is Enectali Figueroa-Feliciano. Not everybody can say that, and that's okay. I go by Tali. It's the last four letters of my name. I am a professor at Northwestern University. I also have a joint appointment at Fermilab, and I'm part of the Quantum Science Center. Today, we are going to take a little trip through the cosmos and end up thinking about how can we use QIS technology to learn more about the universe that we live in. I know, or I am making an assumption that you guys are experts at many things, but how many of you are astronomers? Right. So I'm going to assume that you guys haven't necessarily seen this material before, and please, I know that a lot of these topics are hard and kind of abstract, and if you have questions, just ask, okay? So as we go, feel free to raise your hand, or if I don't see you, just start yelling. Okay, so very high level, we are basically going to go through and talk about the direct detection of dark matter. We're gonna talk about what dark matter is, why we think it's there, and then I'll give you one example. I mean, I could, usually when I've given these summer schools, I have like a 3-lecture series on all of the experiments and all of the techniques. In 1 hour, I can't possibly do that, so I'm just going to focus on one example that has a tie-in and similarities to the type of QIS dark matter sensing that I'll talk about, and then we will talk about qubits for a little bit. Okay, so let's start at the beginning. Cosmology and particle physics are trying to answer the biggest questions, right? How did the universe come to be? How did we get here? What is the universe made of? And in the particle physics realm, we're trying to understand, well, what are the basic building blocks? What are the Lego blocks that make up the universe? And we know that, we have atoms, and these atoms have protons and neutrons, but those protons and neutrons are actually made up of even smaller particles called quarks. And through, decades of work, we've come to understand that the entirety of this building, of you, of us, of the planet, is made up of these three things, of up quarks, down quarks, and electrons. That's it. Everything, your coffee, your hairnet, your shoes, yourselves, everything is made up of these three particles, just arranged in different ways, which is a pretty amazing thing. But it turns out that those are not the only particles that exist, right? There's a zoo of other particles that we call the Standard Model. And one of the questions that we want to understand is, well, why are those particles there? What is their role? And we want to ask the question, are these all of the particles that exist? And that's what the LHC is trying to find. We recently found the Higgs boson. That's the newest particle that we found that was expected to be found, and we found it. But we have evidence that this is not the full picture. The Standard Model is a great success. Like, we are able to predict things to, many significant digits and get the right answer. But we know it's not complete. it does not explain different questions that we see in our universe. One of them is dark matter, and that's what we're going to focus on today. But there are the neutrinos right here. These neutrinos in the standard model do not have mass. The standard model particles, neutrinos, do not have mass. And yet we know that they have mass because we have measured the effects of neutrino oscillations that come about when particles don't have mass, when particles have mass. So we know experimentally, we have verified that the neutrinos have mass. And so in a way, we can say that we've already found beyond the standard model physics, which are neutrinos. The neutrinos that we measure do not behave as predicted by the standard model, which is why neutrino physics is such an interesting field, because it is those are the three actually measured known particles that contain physics beyond a standard model, a verifiable measurement. However, we also know that the standard model would predict that the universe would be a very boring place, because in the standard model, there's no reason that there should be more matter than antimatter. So if the standard model is correct, the universe would just be an empty void, because all of the matter would have annihilated with all the antimatter. And so the fact that we're here tells us that there's something else in the standard model that's missing, that somehow generates the asymmetry that allows matter to dominate in the universe. Somehow, less antimatter was around than matter so that we could be here. We also know that the universe is accelerating, and the acceleration of the universe is nowhere to be found in the standard model. And of course, nothing in the standard model says that I should not be floating right now, and I'm not. And so gravity is completely missing from the standard model. So there's clear things that are missing here. It's not a hypothesis. It is a fact that this is not the complete picture. And so part of our job as particle physicists is to find what is next, what is missing, what's the next chapter in our evolution to understand the primary Lego building blocks of the universe. Okay, so my research centers around the first three, but today, due to time, I'm gonna just talk about dark matter. All right, so why do we know that dark matter is there? Well, the first piece of evidence is the rotation of galaxies. So galaxies are, gravitationally bound groups of billions of stars, and you can calculate how fast they should rotate based on gravity, right? The things in the center are pulling at the same as on the outside. And you can predict this speed at which things are going to be rotating. And when you actually measure, you see that the rotation is much faster than what you predict. And what that implies is that the rotation, if you imagine me having a rock actually shows Rubik's Cube, right, with the string that he was using to do a pendulum. If I swing it around, right, the speed at which I swing it around is going to be connected to the tension on the string. And the faster I spin it around, the higher the tension on the spring. And so by measuring the speed of the stars, I can measure that tension, in which case here is the gravitational force. And that gravitational force is created by the matter between the center of the galaxy and that star, right? Because the matter that's outside does not come into play. And so by doing that, I can basically make a map of how much mass there is, and I can see that the stars are not enough. Now you say, well, there's dust and there's planets, and planets don't shine, but you can take that into account. You can say for each star, let's assume by observations, we know how much non-luminous gas, dust, planets I just add a factor to account for that, and it is just not enough. There's another thing there that is needed that we're not accounting for in our visible universe to add mass to make this work. And we could actually measure this. So this is a really interesting measurement. This is a log scale in kiloparsecs. And just to those of you that don't think in kiloparsecs, 10 kiloparsecs is 2 × 10⁻17 miles. And this is one of the problems with astronomy, is that I can say the word 10⁻17 miles, but I guarantee that none of you understand what the heck that means, right? This is such a big number, 10⁻17 miles, that there's no reference, right? Like it's very hard for our brain to just put that into context. But that is sort of where we are. So this is sort of where the sun is. And this is the center of the galaxy, and you can see the speed. And then this is different components that you need in order to maintain this speed. And this is sort of the edge of the galaxy, sort of the edge of where our gravitational bound is, and kind of where M31 starts. And you guys know that, like, for example, the watershed maps, where you see the watershed of the Mississippi, and this is sort of where water from anywhere would end up in the Mississippi River versus going the other way. That's kind of what this line is, right? If I'm here and I were stationary, I'd fall this way. If I'm here and I'm stationary, I fall that way. Anyway, you need this extra stuff. Now, that's not the only piece of evidence. That's an evidence at a galactic scale. But there are things even bigger in the universe called clusters of galaxies. And so these are, you know, hundreds, thousands, even millions of galaxies. So each one of these little dots is an entire galaxy. And these galaxies are all gravitationally bound together. And you can measure the speed of each galaxy. Now, these are not rotating, like they're just kind of moving in sort of randomish directions, but you can measure the speed of these galaxies. And there's a thing called the virial theorem. And the point is that if you measure the speed of these galaxies, you realize that if you just account on the mass that you see here, these galaxies are moving fast enough that they just go away. It's not gravitationally bound if you just take into account the mass that you see. So again, you can do this measurement. In order for these things to be gravitationally bound, you need more mass. You can even go bigger, and you can say, okay, here is a map of the galaxy. So this is actual data. Each of these points is a galaxy, and you see this kind of filamentary structure at cosmic scales. And here's a simulation of that. And here's, like, you know, these kind of simulations of matter aggregating over time. And in order to make these things look similar, you need to add extra mass. You need this dark matter. So at galactic scales, at clusters of galaxy scales, at kind of big swaths of the universe scales, and even at the further scales that we can measure, which is the cosmic microwave background, we see evidence that you need dark matter. Now, how do I get dark matter out of this splotch of color? Well, this is a map of the residual temperature of the cosmic microwave background. So I've taken out the 2.75 Kelvin main temperature, and this is just it's the temperature. It's 2.75 minus the actual temperature at each point, right? So it's the residuals. And I've taken out, like, well, I haven't, but the team has taken out the galactic emission, which is sort of this gray outline. And what you end up is with this map that shows you small differences in temperature, and you can correlate the scales at which things change. And you can see that things over here and things over here have about the same frequency structure. When you take an FFT of this and you kind of figure out what are the correlations and scales, they're the same everywhere. And the interesting thing is that this is an all-sky measurement, and you need to, like, things over here and things over here are opposite sides of the universe. And there haven't really been talking to each other. And so you get this kind of, this is one of the arguments for the universe being homogeneous, but you can use this to make a model of cosmology. So if you take that and take the FFT of it and do a correlation, you get a curve that looks like this. So the x-axis here is essentially the frequency, called the multipoles, but basically it's a distance. Small, higher multipoles mean smaller distance. So this is like at the biggest scales, this is at the smallest scales, and this is the correlation. You can see that there's structure there. This is not just some random, like, this is not TV noise, right? It's not just white noise. There's a structure there. There's a special scale that is more strongly shown than others, and that is what you're seeing here. And the amazing thing is you can fit this with a cosmological model that only has 6 parameters. And that model tells us that there are different components that make up the universe. In this plot, you have the CMB is this orange thing here, and the x-axis is the amount of matter in the universe, and the y-axis is the amount of dark energy in the universe. And this confluence of measurements from supernova, from barrier acoustic oscillations, and from the CMB point at this little dot right here, which is sort of what tells you what the answer is. And this is another plot that is looking at the components of lithium and helium and deuterium that were made in the Big Bang. And they're fairly consistent with this model as well. And that model basically tells us, that's supposed to be a circle. That model tells us that our universe is made up of these components. And so there's this thing called dark energy that makes 68% of the universe, dark matter that makes 28% of the universe. Then there's gas, hydrogen and helium that makes about 4% of the universe. Then there's like stars and gas in between the stars. That's this little red wedge. Then there's neutrinos, and that's this little purple wedge. And then the little black line is the heavy elements, which means things above, lithium. And that's all of us. So in this 0.03% of the universe accounts for all of the planets, all of the people, and much more importantly, all of the ice cream in the universe is contained in that one little bit, right? And that's a pretty amazing thing, like if we want to think about like our evolution from like our anthropomorphic, humanistic center of the universe view, this is the ultimate put down, right? Like we're this little itty bitty bit of what the universe is made of. So before these measurements were made, we really thought that the stars, like this red and this black stuff here, was the entire universe. And so it was a huge change in our view to understand that these two things, dark energy and dark matter, make up 96% of the universe. And so, we really did not understand the power of the dark side. So let's focus on dark matter. All right, how do we, so there's some evidence that it's there. Any questions? Yes, please, before we go on. The gray lines? So the gray lines, so that's just the galactic plane. So this is the center. These are galactocentric coordinates. So this is the center of the galaxy. And the galaxy is a disk. And so this is the disk of the galaxy. These are spurs, like gas that kind of blobs out. And so basically what these gray parts are illuminating is that when you look at the scale here, this is in microkelvin. So this is a residual plot. The actual data is this super red, very hot thing in the middle, which is our galaxy. And so they've subtracted that. And they keep that there to say, we trust this part a lot. This part is a lot harder because they're subtracting a lot more stuff there because it's a lot brighter there. So that's just to kind of give us an idea of where our galaxy is in the sky map. Okay. So yeah, so let me go through these numbers. So the cosmic microwave background are made of photons that were made when the universe was 380,000 years old. So this is T after the Big Bang. And they're free streaming. So these are photons that have been going through space. When they were emitted, the energy in the universe was 10 to the minus 10 GeV. That's about 3,400 Kelvin. But because the universe is expanding, the wavelength of the photons expands with the universe. And so a photon that started with a short frequency that corresponded to a temperature of 3,400 has expanded as it travels through an expanding universe, and it's now at 2.7 Kelvin. So 2.7 Kelvin is the temperature. There's a black body temperature that you get from the CMB, and it gives you that number. Now that has been subtracted, and this is what's left after you do the subtraction. So this is really a residual plot. Okay. Other questions? Previous slide. Speak louder. I can't hear you. Sorry, you got to speak up. I have a plot, yes. This one? This guy. Okay, so I am asking the question. Let's say that I pick a distance. Let's say that I pick this distance. And I can take a blue spot and I can go, okay, from this blue spot to this red spot, I see that I go from blue to red. And then about that distance. And then if I go over here, I say, okay, I'm at another blue spot. How far do I have to go to get to a red spot? And hey, that's about the same distance. And then I go over here and I say, how far do I have to go to get to a red spot? And hey, that's about the same distance again. See the correlation? So that's what I'm plotting. Each of this x-axis is a distance in the plot. And I am asking how often, when I move that distance in the plot, do I go from blue to red? And that gives me a magnitude of change. And what I see is that at certain distances, I get a lot of change. At certain other distances, I get less change. Yes. So each of these, so this is basically, I'm trying to condense the cosmology course into an hour or so. So if you take the cosmological model, there are, if you look for Wayne Hu, there's a really good cosmology primer that has this plot and it has levers on it on the web. And you can change the amount of dark matter, the amount of dark energy, and these things move around. So there's a model of cosmology that predicts the shape of this thing. And by fitting these points, you can then pull out those 6 parameters that I talked about. Yeah, so one of these is like the matter peak and one of it is the dark energy peak. So like, and they're not exactly like dark energy will make the first peak big, but the second peak not necessarily as big, and then dark matter change. They all move this thing around in slightly different ways. So it's just think about it as a polynomial fit, and you have different coefficients, and you're just messing with the different coefficients. It's just a way more complicated equation to get to. Okay. Yes. Sorry. Let me get him first. Newtonian dynamics. Yes. Using dark matter. Yep. And I'm just curious if you could. Sure. So the question is MOND. It stands for what does it stand for? Modified Newtonian dynamics. So the idea is that, hey, maybe dark matter is not there. And if I look at the galaxy rotation curves, maybe I just need to change gravity, right? Because I'm making this argument about the string, right? And the tension. And I'm saying that the tension is due to gravity, but if I just change the equation for the tension, then that could explain why the tension is what it is, right? The problem with MOND, and we were having actually this discussion in lunch yesterday, the problem with MOND is that it does not explain this. It does not quite fit into this. And it doesn't very well explain the large scale structure and the clusters. It explains the galactic rotation curves really well. And then you need to start throwing in more weird things to explain the other things. So the statement I will make is that we do not know that dark matter is there for sure. And there are other alternative explanations. But dark matter is the theory that best fits all of the available data at all of these scales. All right, somebody else had a, yes.
So I mean, it's not the definite this 6 parameter generates data set.
So sorry, what is the question? Mm-hmm.
So we have a manifold.
Sure.
Yeah, so how does that fit it?
I mean, I don't have the like fitting, but you know, basically you're going to end up with some region, right? Like it's just like anything else. You don't say dark matter is blah plus or minus blah, right? So any of the points in here are a good fit. And so you can make constraints on the parameters. Yes. Yes. Is there a say the question again?
Why the error bars are so deep for the beginning of the
Yes, because error bars, you know, when you're calculating your error bars, what is one way of getting your error bar smaller? Making many measurements of the same thing, right? And if I think about this map and the high numbers are small distances, I have many measurements of small distances. But these are the large distances and I only have one universe. So I can only make so many large distance measurements. So that's why my error bars get big. All right. Let's move on. So what does dark matter need? So what do we know? What do we know? Well, we know that dark matter is cold. Cold meaning that it's non-relativistic, that it has to be slow enough for allowing things to form. We know that dark matter is, if the dark matter theory is correct, dark matter is this glue that's really making galactic formation happen. And it can't, and in order to do that, it has to be cold, so it allows things to kind of fall into it. It can't be like photons moving at relativistic speeds. We know that dark matter is not made up of quarks, of protons and neutrons, and we can know that by looking at various pieces of evidence. One is just like looking at the amount of dust, looking at the composition of the elements in the universe, just from the cosmology parameters. Dark matter being dust does not work. You would be able to see it if it were, it would block out light. Like there are other tests that you can do that show that dark matter cannot be baryonic. We think it's a particle. It might not be a particle, but we have good reasons to think theoretically that it's a new particle, as we were talking about, rather than a modification to gravity, right? It could be a modification to gravity, but that is the best fit to the data. Now, we also know that it's dark. And when we say dark, it means that it doesn't interact with photons, right? Because we don't see it glow. We don't see it in our telescope. Now, that doesn't mean that it cannot couple to the photon, because for those of you that have taken quantum field theory, you know that what this means is that at tree level, right, there isn't a connection between the particle and a photon, but you can always go through virtual particles. So you can always make a loop that will go from the dark matter to something, as long as it connects to anything, right? Then you can say, well, that something can then connect to something that can connect to a photon. So it just means that the cross-section, that interaction term is extremely low. It could be zero depending on the theory, but it doesn't have to be zero. It just has to be zero at tree level. Okay, so why are we so interested in dark matter? Well, first of all, it makes up 24% of the energy density of the universe. It's actually 80% of all of the matter in the universe is dark matter. And so we really want to know what it is. But also, well, we right now are trying to figure out what's beyond the standard model. And we don't really know where dark matter fits in. And if we find dark matter and we can understand its properties, then we can start to exclude many of the theories that we already have about what dark matter is. And it can lead the way, point the way at what is beyond the standard model. So it could actually be a key that allows us to understand not just dark matter, but physics beyond the standard model. What framework is the right framework for us to be able to understand physics beyond the standard model? Okay, so I hope that I've convinced you that this is a really beautiful problem in physics. It spans 40 orders of magnitude in scale, from the largest scales in the universe to galactic scales to particle accelerators where we're trying to make dark matter. And so we're going to then talk about, okay, let me, I guess, stop here and ask if there are any other questions about kind of the general cosmology, because now I'm going to switch over to talk about how can we detect dark matter. So before we do that, are there any other questions? Yes. Okay, I did not say there is no evidence. I said that I am postulating that dark matter is the theory that best fits the available evidence. So what I'm saying is, as a scientist, look, we're all, what can we ever say something is true? As scientists, our job is to say, what is the model that best fits the data that we have? And the data that we have best fits the dark matter model. That doesn't mean it's right. But at this point, with our available information, that is our best hypothesis. There are other hypotheses that might end up being right. But at this point, this is the best one. And so we move forward making that hypothesis, not postulating that this is true, just saying, this is the best hypothesis we have. So let's continue investigating and see if we gather more evidence that points to this being the correct answer. Well, if the next best, I mean, basically, either dark matter is right. Let me think about that for a second. I think the next best thing is something related to MOND. Basically saying there is no dark matter and you have to modify GR to account for what we see. The problem is that nobody as of yet has come up with a self-consistent GR theory that can fit all of this data. MOND can fit the galactic data, but MOND is not a GR theory. There have been attempts of building a GR theory from MOND, but as far as I understand it, those theories do not completely work.
But like all the characteristics that you said, like cold, does like, I know that it is, people believe that it axioms, winds, and maybe primordial black hole, all of them can
Fit, yes. All of the theory, yes, all of the, and I'm gonna go have a slide on the dark matter candidates, all of those fit that bill. We'll talk about that in a minute. Give me some slides. Who else? Yes.
Dark matter doesn't couple to at tree level. Do we know what it could couple to at tree level? Like what is the
Ooh.
dark matter?
So the question is, what does it couple if it's not at tree level? That, if you go to the archive and you say dark matter theory, you will get about 1 billion hits. And each of those has a different answer to your question, and each of those claims that they are correct. Okay. So how do we find dark matter? Well, basically, if we think about the basic dark matter Feynman diagram, if this is dark matter, chi, and we have a standard model particle, Q could be a quark, could be a lepton, just a standard model particle, then we are just looking for some interaction where the dark matter interacts with the standard model particle through some mediator and then keeps going, right? And that is basically a signature of a collision where a standard model particle comes in, a standard model particle comes out, dark matter comes in, dark matter comes out. That's called direct detection. But you could also think about having time go down, and then you can have a standard model particle, dark matter particles annihilating in some way and generating standard model particles, right? And so that's annihilation, indirect detection. We can detect the standard model products of some process that happens with dark matter and some other potential particle. Or if we go this way, we can say I start off with standard model particles, and if I whack them hard enough, I'll generate enough energy that I will make dark matter particles, right? And so that is production. And so all of those are viable ways of searching for dark matter. We're going to concentrate on the bottom one today. Okay, so there's only a few theories of dark matter. And this is an attempt by Tim Tate to organize the theories, and you can see what happened. Basically, he just ended up with a spaghetti bowl. So there are many, many different theories, and you have to sort of go through this menu and ask, well, how would I be able to determine which of these theories is correct? And you have to organize it somehow, right? So the way that we're going to do it is by mass. We do not know what the mass of we know dark matter has mass. That's one of the requisites, right? Because if not, it wouldn't be dark matter. So let's organize it in terms of mass. So I can make an axis that's mass, and then I can say, okay, I have all of these different dark matter candidates. I have axion-like particles, I have axions, I have sterile neutrinos, I have WIMPs, I have a whole zoo of particles from hidden sectors, and there's many others that I'm not putting here. And then you can say, okay, well, how can I detect these things? And so one of the things that, you have a detector, you have a standard model, set of particles, and the dark matter is going to hit them. How does it hit them? Like, what is the actual interaction? Well, one of those is a nuclear recoil, right? There are atoms in our thing. The dark matter can come in and hit one of those nuclei. So we have nuclear recoils. And if we're looking at nuclear recoils, this is the energy range or the mass range of the dark matter particles that we would be able to sense. Now you can ask, well, what's setting the bounds of that? Why can't I sense heavier particles? Why can't I sense lighter particles? Well, you can take a target, for example, silicon, and do the kinematics. If I have a dark matter particle of this mass, we kind of know the velocity because we know it's cold, we know the size of the galaxy, we know where the Earth is, we know the average velocity and the velocity distribution of dark matter in this room. And there's dark matter going through this room right now, right? And so I can ask, well, what is the recoil energy that I get when I have one of those dark matter particles hit my device? And you can see that for heavy particles, I get a lot of energy, 10 to the 5. Great, that's easy to see. As I get smaller and smaller in mass, I see that the kinematics, the nucleus has some mass. So if I make the mass of the dark matter smaller and smaller, it's more like throwing little ping pong balls at a bowling ball, right? And so the mass, the energy that you can put into the target starts to go down. And so it gets small enough that it gets hard to see. Now, why can't you just keep going this way? Well, we know how much dark matter there is because we measure this rotation. So we know the dark matter density in the room. We know how much dark matter there is in per cubic meter, how much energy density there is in dark matter. So as you make the dark matter heavier, if we know the density, that means that there's less particles, right? So the number of particles depends on the mass. So the number of particles per liter depends on the mass because the density stays constant. We know what the density is. So as I make the particles heavier, I need less of them to get the density. And so I get to the point where there's so few of them that my detector just, will have a hard time seeing them. Whereas when I go over here, there's many more of them, so it gets easier to potentially have an event, but the energy gets smaller, so it gets harder to detect. Say it louder. Because once you get to the kinematic limit, you just are always giving the same energy to the particle. So it's just a fact of saying that now it's like a bowling ball hitting a ping pong ball. Okay, now we are missing a whole bunch of stuff. So we want to fill in this. So what can we do? Well, the problem with nuclear recoils is that they're heavy, right? So they're good for heavy dark matter. So if I want to do lighter masses, I want to use a particle that has less mass so the kinematics are better. And one such particle is electrons. So I can do electron recoils. And if I think about electron recoils, then the kinematics are much better for lower masses. And I can go all the way down to here, to about keV dark matter. Now, as we start going lower and lower in mass, remember the density stays the same, so the number of particles starts getting pretty big, right? Because the density is constant. As I go to lower and lower mass, the particle density gets very, very big. And I can think about particles, dark matter particles, having, of course, both a wave-like and a particle-like nature. So at some point, the dark matter particles are the quantum, their wave functions are going to start to overlap if there's enough of them and they're close enough. So I can plot what is the mean distance between particles. Instead of how many there are, how close are they to each other on average? And then I can write down what their de Broglie wavelength is. And what I find is that there's a point in which the distance between the particles as I go down here and the de Broglie wavelengths start to match. So basically they're so close that their wave function extensions are starting to overlap. And that happens at around an EV. And that's the line between particle-like dark matter and wave-like dark matter. So when you have dark matter that's way over here at very small masses, there is tons of them. And so they're very close to each other while their wavelength is very big. So they're completely overlapping and they act as a wave. Does that make sense? So this is the weird thing about quantum mechanics, right? We have wave-particle duality. If the particles have a big enough wave function, they're close enough, they end up just all meshing together into this one wave. And so the idea is that then you have coherent effects that you can then look for. And most of the axion searches are looking for these coherent effects. All right, so how am I doing in time? Okay, not great. All right, so I'm going to focus only on this stuff because I don't have enough time, and talk to you about some of the work that I've been doing. So let's talk about this bowling ball versus ping pong ball problem, right? So if the dark matter, if I have a nucleus and I have a very light dark matter particle and it hits my nucleus, as I go to smaller masses, the amount of recoil energy that I get, so this is the amount of energy that I get in the detector from a dark matter particle whacking into it, goes down. And so this is like 1 GeV dark matter, 500 MeV dark matter, 200 MeV dark matter, and these are KeV. And so when you go to, you know, these sort of, this is 1 EV over here, this is really hard to sense from a detector point of view. And so it gets harder and harder to see this low mass dark matter. So we can think about this in a different way. So if this is the mass of the dark matter, and now in MeV, just to make the scales a little bit better, and this is the maximum recoil energy we can get from a dark matter hitting, then we can make some plots about if I have elastic nuclear recoils, if I think about like what's the maximum energy through inelastic means. And I'm not going to spend too much time talking about the specific effects, but basically we can make these plots that have the energy that we can get out of a specific mass of dark matter. These maximum energy things require more sophisticated things like this Migdal effect or collective modes of phonons and magnons, which is actually where we're going to be thinking about for our qubits. We can then say, okay, well, what technologies can I access that have enough resolution to be able to see an event of that energy? And it turns out that, you know, the xenon, argon, helium detectors, like they can sense things at about these recoil energies. Then you get to ionization in semiconductors, so lower band gap structures that can see sort of 1 EV recoils. Then you get to optical phonons or low gap materials. These are like things like we were working on Splendor, which was one of the things that we're working through QSC. And then you get to superconductors, superfluids, or single phonon detectors if you're trying to sense this like very small kind of milli-eV recoils. And so if we want to be able to search over this entire mass range for dark matter, at some point, we will want to be able to do things down here. We need to get to this, point. And this is where quantum sensing may come into play. So, right. So let's look at an example of what a dark matter detector currently looks like. And I'll go through quickly because we're going to run out of time. So this is sort of what the state of the art is. We've been working on these detectors for like 20 years. This is called a transition edge sensor. So if you have a superconductor, you have the temperature of the superconductor, and this is the resistance of a thin film of superconductor. At some point, it goes into its critical temperature and goes to zero resistance, right? That's superconducting on the left, normal metal on the right. And if you operate the device right at this transition, a small change in temperature is going to make a big change in the resistance. And so you get a good transduction between temperature change and resistance change. And so if you operate your device at the transition, you get a really good thermometer. And that's the basic idea. And then we connect that to our target, and then we measure the temperature of the target. And when a particle hits the target, we actually see the heat deposit in the target as a spike as this thing goes up and then cools back down because we've refrigerated it to like 10 millikelvin. And so it goes up and it cools back down. Okay, so we have superconductors, we have cryogenics. In order to read these things out, we use SQUIDs, so superconducting quantum interference devices. And as many of you know, these are made of Josephson junctions. Many qubits are made out of SQUIDs. So now we have dilution refrigerators, superconductors, and junctions. Hey, there's a map. This is what one of our detectors looks like. There's a target, silicon crystal. We have Cooper pair breaking aluminum, and then we have our TES. And the idea is that like each of these little rectangle things looks like this. This little gray line in the middle is the transition edge sensor. And then these are basically like catcher's mitts. They're superconductors, they're aluminum superconductors. Phonons rattle around and they whack into the aluminum, they break Cooper pairs, that energy goes in, diffuses into the TES and heats up the TES. And it makes the TES get warm, and we sense that. And we put a lot of them on the surface and just basically gang them up in parallel into channels that we can then read out. And so the way that this works is like if you have a particle, it comes in, it creates phonons, and it creates electron hole pairs. For some of our detectors, we put a voltage across them, so there's a field, and that drags the electrons and holes through the crystal, and that generates more phonons because it's an insulator. And if you're moving a charge through an insulator, you need to do a certain amount of work. And that work is just Q times delta V. And that Q times delta V work becomes energy in phonons. And so you gain energy by doing this. And these are called NTL phonons, negative Luke phonons. The point is that we have a way of measuring the energy that gets deposited, and depending on whether we put a field or not, we can enhance the signal from the electron hole pairs that are made. It is just a way of getting a better detection. And this is what these detectors look like. They're about 1 or 2 centimeters. And we've been developing this with my colleagues. This was designed at Northwestern and put into our fridge. These detectors can see single electron hole pairs. So we can detect a single electron hole pair, 2 electron hole pairs, 3 electron hole pairs. So they're really, really nice detectors. We've published a couple of papers on them. They have one of the best resolutions. This is actually old. We now are like below an EV. We have a calibration over a very large energy range. And we're using these for dark matter. So we're running this at Fermilab. So we have this underground experimental site that I'm the PI of. It's this clean room right here. We are using this for a lot of QSC work, and QSC also funded a second, basically a sister version of that called Quiet that is actually being commissioned right now. We just had the ribbon cutting a couple of weeks ago, and my grad students and my Fermilab colleagues are there yesterday and today installing hemps and other things into the fridge. So we now have 2 facilities underground. We're 300 feet, 100 meters underground, and this cavern gives us low radiation, low cosmic ray background to work on. Inside the Nexus, we have a dilution fridge, and we can put our devices here. We also have a calibration source with a neutron generator that we can use to throw neutrons at it to do neutron calibrations. And then we have gamma sources that we can use. We have a qubit testbed where we're testing the effects of radiation on qubits. And we then have our dark matter testbed. So these detectors have been run at Nexus. This is a picture of the first setup where we were doing 4 of these detectors, and we realized that the mounting of the detectors were actually fluorescing. So it was made of just a PVC kind of material, and the carbon and the silicon oxide on the material was fluorescing. And so we changed the design to a material that had very small amount was all copper with very little amount of insulator. And we went from this pink spectrum to this purple spectrum. So we were able to kill a whole bunch of this background by removing all of the scintillating material. We actually just published the pink data, just came on the archive, and we're preparing to publish the better purple data, which we expect will have a world-leading sensitivity to dark matter. Okay, so that is sort of an example of where we are. So now let's talk about how do we get to here. So this is part of QSC work from Thrust 3. I'm not going to talk about qubits because you've seen the Bloch sphere a billion times, but I will go over a couple of different papers that have demonstrated the effects of radiation on qubits. So if I want to now think about a qubit and ask the question, can I use a qubit or a qubit-based technology as a detector for dark matter? So one of the first questions is, well, does a qubit do anything when you whack it with energy? And so that's a good question. And there are a couple of papers showing that that doesn't happen. So for example, in this paper, there's a qubit chip and there's a radioactive source that was placed inside the resonator right on top of the qubit. And this particular radiation source was prepared so that it has a very short half-life. In other words, the strength of radiation coming out decays rapidly over a couple of days. And so they can actually plot the T1 or 1 over T1 as a function of time and see that T1s were low and they get longer as a function of time, and that time constant corresponds to the time constant of the decay of the radiation source. Right? So that's a good example of a correlation between the T1 time of a qubit and the amount of radiation it's seeing. And basically, we have this picture where we have a bunch of energy being deposited by gamma rays or X-rays, and these are producing phonons, are breaking Cooper pairs, And then these excited quasi-particles are tunneling through the Josephson junction, and those tunneling events are causing decoherence in the qubit. And this was this made a splash when Google showed this paper where they were showing catastrophic errors from cosmic rays, where a bunch of their qubits would basically start, their T1s would drop dramatically for milliseconds at a time, and they were correlated errors, which is very important because if you're trying to do error correction code, you do not want to have a correlated error where a bunch of your qubits go down at the same time, right? So this is a major problem for quantum computing. For us, when this is a plot of the number of qubits that have errors, or the number of simultaneous qubit errors as a function of time, and then these, you can see that you got a bunch of errors happening, and then the number of errors goes down. This looks like a signal to us, right? That looks like a pulse. So this is a way, maybe not the best way, but this is a way of using a qubit chip to detect radiation. And so they published this paper. They show the Sycamore chip. This is kind of the chip layout. This is the figure that they have on their Josephson junction with their phonons and the gamma ray going through. And this is the Google system. And then I looked at this and like, wait a minute. These things look very similar. We got this, right? We have detectors that are about the same size. They have superconductors on them. We have basically the same process between like gamma rays and quasi-particles and aluminum. That's exactly how we're doing dark matter. So we are really saying there is a very interesting connection here, and that's what we're trying to understand. All right, how many minutes do I have? 10 minutes? Okay, I'm good. All right, are you guys okay? Not falling asleep? All right. So, we can kind of think about superconducting qubits for quantum computing, superconducting qubits for dark matter, what things are important, and there's an overlap where studying the error rates and the effects of radiation and quasi-particle poisoning, understanding phonon transport. All of those things are important for both. And then there are aspects of them that are more important for one or the other. But I think this is an interesting place to be as a researcher that is doing particle physics. Can we bring in some of this QIS technology and do something in the field of dark matter? So let's think about it. If I want to make a qubit sensor, one of the first things that I have to ask is, well, what's my signal? What am I measuring? Right? And so you can think about, like, what is it that I'm going to actually look for? Like, I have my qubit, I have some substrate. I'm going to assume that I have dark matter whacking into my substrate somewhere. Well, what can I measure? Well, I can measure, I know I can see changes in T1. I might be able to see changes in T2 or some other performance metric. Those tend to be hard because to measure T1, as you guys know, you got to measure it, many times. And it's a question of how efficient that is. And we're going to talk about that in a second. You can measure changes to parity. As quasi-particles jump from one side of the qubit island to the other, it changes the parity. And so if I'm doing parity swap or parity measurements, I might be able to see those events happen. I can measure the quasi-particle density. If I can measure the quasi-particle density in my qubit islands, when we have an event, I should see the quasi-particle density go up because I'm breaking Cooper pairs and now there's a whole bunch more quasi-particles. I can do state changes where I prepare state and then see if it changes into another state. I can look for frequency changes. I can think about entangling qubits and looking for signals that are that change due to the entanglement when phonons react with the qubits. I can think about collective phonon modes that are, in the substrate, and think about qubits as a way of sensing those collective phonon modes, right? So there's many different avenues here, and it's not obvious to me right now which of these is the best, right? That's part of the if we knew what we were doing, it wouldn't be called research. And then, there's hybrid devices. We already have TESs, we have things called SNSPDs, we have MKIDs, there's all these other detectors. Maybe the right answer is actually to make a hybrid device that has both qubits and MKIDs, or both qubits and TESs, and be able to distinguish different signals to look for backgrounds versus dark matter. And that's a whole other thing that I'm not going to have time to talk about. So we've been measuring charge-sensitive qubits at Nexus. We can see, basically doing some Ramsey tomography. We can look at the state of the qubit as a function of applied offset charge, and it follows this curve. But then if an event happens, it changes the amount of electron hole pairs in the substrate, and that changes the overall field, and that affects the qubit because it's a charge-sensitive qubit. And when that happens, we see that this pattern changes its offset. So the offset that we need, like the phase of this thing, abruptly changes and goes from the blue one to the green one. And then another event happens, and we've changed the phase again, and it goes into this orangey red one. Right? So we can use this as a way of actually detecting hits in the substrate. And so this is a possible detection mechanism. Question? No, this is data. Yep, the lower platoops right here.
Okay. So like, is this scientific emission?
Nope, these are gamma rays hitting the chip.
And so to detect dark matter, you would like shoot.
Yes, so obviously we don't have a dark matter beam to test our detector with. So in order to test our detector, we use gamma rays and neutrons. Neutrons are better, and which is why we have the DD generator at Nexus. We start out with gamma rays because that's the easiest thing to do. But then when you want to really simulate, okay, what does a WIMP or a dark matter particle look like, you would use neutrons. But this is just calibration data, yeah, just to show the idea. Okay, we are also working on this paper. We're working on simulating this. There's a particle physics software called GANT4 that tracks particles, and there's an extension of it called GANT4 CMP for condensed matter physics. And that software can model phonons and electron hole pairs in substrates, and we're using that to model how qubits, we can, instead of putting sensors on the surface, we can put qubits on the surface of this model and basically model the response of qubits to an event. And this is an entire talk. But there's a paper on this that you can look at. This is a QSC postdoc, Ryan, from Fermilab, Ryan Linehan. Okay, so one of the problems with this is that qubits are tiny. Junctions are tiny. And so how do I get the energy to the junctions, right? So there was this paper by the Google, I think, guys, that is doing this gap engineering where they are changing the thicknesses of the aluminum to change the TC, which changes the energy levels. And they're using that to prevent quasiparticles from crossing the junction in two directions to get better coherence times of their qubits. Okay, so the idea is that if I have energy levels across my junction, I can have quasiparticles go both ways. But if I go like this, then quasiparticles go this way, and then they can't go that way. And so you stop the jumping around of the quasiparticles and you get better coherence. Well, what if you yes? we have, so one, we have a gamma ray source and we can match the rate. Two, we have a separate detector that is a gamma ray detector that's also seeing the same spectrum. It's not seeing the same events, but it's seeing the same rate. And three, we can kind of match the kind of spectrum of the gamma rays that we see and the rate to the number of jumps we see in the qubit. So some of them could be from TLS jumps, but we are pretty sure that what we're looking at here, like we have a shield and we can pull it out and in and see the rate change when we pull it out and in, and that wouldn't happen if it were TLSs. So this is a paper from Noah Korinsky, Hannah, who is over there, is actually building these things. So if you want to talk to Hannah about squats, go ahead. So the idea is, well, look, in Super CDMS, I didn't go into it, but remember I talked about these aluminum structures that act like mittens and they catch the phonons and then they funnel them to the TES. That's gap engineering. We invented that like 20 years ago. They just changed the name. It's branding. It's the same deal, right? You change the TC and you funnel instead of using gap engineering to prevent the quasi-particles from going to your junction, you do the opposite. You make a valley so that quasi-particles diffuse in and then they can't get out and then they go to the junction and then they're there and they do a lot of interaction. So Noah and his collaborators have written a paper on this. And I will point you to that paper because I'm running out of time. But the idea is, can we use basically something that's extremely close to a qubit to really sense these jumps in quasi-particles crossing the junction? Okay, so as I said, we're really just starting this, and there are many ideas of how one could do this. And it might be that we want hybrid detectors that have MKIDs and junctions in the same device. We don't know yet. But it's an exciting field. And for those of you that are more interested in kind of the sensing aspect, come talk to me, talk to Hannah. There's a lot of other people here that are working that are working on this. And I think it's a very interesting development to try to really both understand how to control and design interesting devices, because the knowledge that we gain through that can also be applicable to doing better qubits. If I have a knob that says I can increase or decrease the sensitivity of my qubit to incoming radiation, I can turn the knob one way to make it into a gamma ray detector. I can turn the knob the other way to make it into a quantum computer that's insensitive to gamma rays, right? So understanding how to design these things also tells you how to undesign these things to be, favorable or unfavorable, so that you can then use that knowledge in your qubit design for quantum computing. All right, so that's it. We're looking for the big questions, and this is kind of a field that's wide open. There are many different ideas. I haven't even touched axions, which is an entire other talk about how to detect axions in these collective resonant modes with qubits. Qubits actually are very well coupled to that as well. So there are many avenues. If for those of you that are interested in kind of doing both particle physics and QIS, it's actually, there's a lot of work. There's a lot of opportunity. And thank you for your time.
So I have a very simple question. So how do you distinguish from the signal that these are axions or these are other type of cosmological radiation?
Yep. So the question is, how do I know I'm seeing dark matter? And that's a very good question. The answer is, it depends on the technology, but it boils down to basically two different strategies, maybe three. First one is you have particle ID, like you have some way of telling the difference between a photon, a nuclear recoil, or a dark matter particle. That's kind of hard. Normally, what we have been able to do is to tell the difference between electron recoils and nuclear recoils. And if you're looking for WIMP-like dark matter, nuclear recoil like dark matter, then you can throw away all the gammas because all the gammas are interacting through the electromagnetic force through your electrons. If you're looking for electron recoil dark matter, then that doesn't no longer work. So then you go to stage two, which is, well, I can try to remove all of the gammas from my environment. And that means I need very low radioactivity materials. I need to be underground to get away from cosmic rays. I need to have shielding all over the place to prevent all of the uranium and thorium on the walls that are decaying and giving me gamma rays and neutrons to get to my detector. So it becomes a low background question. And there are, large efforts. People have spent many, many years, and we can build experiments that have a very low background. And what it then becomes is a question of statistics. You can't tell event by event whether this was a dark matter particle or not, but you can say, I understand my system, I understand my background, and I expect this spectrum from the background. If I see a hump above what I expect, that is a potential dark matter signal. How would you say for sure that that's a dark matter signal? Most likely you build a second experiment with a slightly different technology, but now you have a region of interest. You can say this dark matter looks like it has this mass and this type of cross-section, and then you build a second experiment to try to see if they see an excess, and does that excess match the parameters of this one? And can, just like in cosmology, we have these different bands, right? You have CMB, you have BAO, and they all coalesce in some region, and that tells you what the cosmological model is. It's the same idea. We would have different technologies that are coming at it. This is such a big question. No one experiment is going to be able to claim that they see dark matter. They might have a very strong hint, but then we're going to want to build more experiments to corroborate, and then we'll start making those combined analysis. And if enough evidence is found, it's like, look, we have been able to take enough data that it is extremely unlikely that some other background can match all of these different experiments, and then we can claim a discovery.
For example, for the dark matter, isn't the intensity of it doesn't change, or like the quantity of it doesn't change from different locations on Earth?
Okay, so the question is, does the dark matter change in different locations on Earth? Not really, because the Earth is teeny tiny, and the galaxy is huge. So the flux of dark matter is not expected to change at the scale of the Earth. But there is a really interesting thing that happens, which is that the galaxy is rotating, and dark matter is not expected to be rotating with the galaxy. It's probably more just kind of going like this with a very small radial speed, which means that our Earth is moving while the dark matter is moving this way, the Earth is moving that way. And so from the perspective of us, we actually see dark matter coming from a specific direction in the sky. That's called directional detection. So if I can actually detect the recoil angle, like if I can say what angle was the dark matter coming at, I can actually separate that from other backgrounds. And it actually changes as the time of day because the Earth is rotating. So the angle at which, if I'm in the lab, the dark matter is actually processing as a function of the day in which direction it's coming into my lab experiment. And so if I can sense that, and there are a lot of people trying to do that, that would be a really good detector, because there's very hard to get a gamma ray to run around your room in that particular, and give you that signal, right? So it makes it a lot easier to disentangle the dark matter signal from other things. Yes. Magnetic detectors, yes. So there are things called MMCs. One of those M's is for magnets. So there's a thing called an MMC, and I'm blanking out on what MMC stands for. Yes, there are magnetically based detectors where you put a current through a meander, and then you have some local magnetic field, and the current changes when the thing heats up as a function of the magnetic field. So there are detectors based on magnetic field technology. There's other ones too, but look up MMCs on like MMC dark matter, you'll find it. Yes. Because it doesn't couple to gas, and the idea is that you have these big filaments of dark matter, and the gas is falling into the dark matter halo, while the dark matter particles don't interact with each other, and they just go through everything. So they just gain a lot less angular momentum than things that clump together and kind of end up just forming chunks of things. So it's not an obvious, like maybe that's not a satisfactory answer. I would say the modeling of dark matter halos tells us that they don't end up with a lot of angular momentum. And part of that has to do with the fact that there's no friction, right? I think a lot of the angular momentum that you get is because there's friction and things like clump together, and so they slow down and they kind of start rotating, whereas dark matter is just going like this all the time. They don't see each other, they just pass through everything. That's maybe not the best answer, but I would say it's an outcome of the modeling that people do on dark matter like mechanics, so the large scale structure of the universe. Yes. Do I have sensitivity plots? I do. I can show them to you afterwards. Yeah, I have a bunch. I didn't want to go into that, but so sensitivity plots means like if I have a mass and I have like the cross section, what parts of parameter space have been excluded and what parts of parameter space are available. Yeah, we can talk about that offline. Yes. Okay.